Hi, my name is Henry Lee, and for the Quick 5 video, I'm going to be covering attention blocks or attention. As always, I'm going to base my video on a video made by the YouTuber 3Blue1Brown called Attention in Transformers Step-by-Step DL6. To recap, a transformer is a type of neural network that takes a piece of text and predicts what comes next in the passage. As you can see to the right, we're given a passage and they split it into pieces called tokens. To, they, comma, clear, da, clear, veres. And each of these tokens have an embedding assigned to it, which is like a list, a vector of values that somehow encode the meanings of the words or tokens. One of the components of the transformer is the attention block, which allows the model to move information encoded in one embedding to that of another. So as you can see, all of these are like somehow influencing the embedding of this one, like passing information to the embedding of this one. And this is the key for how a transformer predicts what comes next in a passage. After passing information from like all the tokens to one specific token, that one token will have enough information to convey the whole story. And that last word, or like the embedding of the last word in the passage, will have all the meanings of the previous words. So it have the whole story already in mind, and it could predict what comes next to complete that story. But let's say that we only want certain words to affect the last word. We don't want all of it. We just need like specific words. To achieve this, we use a single head of attention. And it is a way to refine embeddings based on specific words. For example, if you have a word creature and this adjective fluffy and blue, you only want those two words to affect this creature. You don't want this whole story, all other words to affect creature, only these two specifics. Well, it would be like a word asking, like, are there any adjectives in front of me? Or imagine a word asking, are there any adjectives in front of me? We can turn that question into another vector called a query vector. And as you can see, the way we get a query vector is we get embeddings, or like that list of values, and we multiply it with a matrix Q, which is like a query matrix, basically. And after multiplying the embedding with a matrix or query matrix, we get the query vector. At the same time, we use the same embeddings and we multiply with another matrix called a key matrix. And when we multiply the embedding with a key matrix, we get a key vector. It's similar to query and keys. They're both similar. And the query, okay, if the query is the question, then keys are the answers. So to measure how well they match, we find the dot product of the query and the key. And basically, the bigger the dots or the larger the values, it means they're more aligned, so they matched each other. So as you can see, the query of creature matches with a key of fluffy and blue, like the fluffy blue creature. So it matches. That's why the dots are big. But like, there's a problem with this, that the values can get very big, can range from anywhere from negative infinity to positive infinity. And we want to normalize these values so that they're between 0 and 1. That's why we use softmath, as you remember from the previous video. But then we still have another problem. It doesn't make sense for later tokens to influence earlier tokens. So as you can see, we don't want fluffy or blue or creature to influence A, which comes before it. Or like any other word, for example, like the, we don't want the to influence A fluffy blue creature run because it, that we are in half the values of those tokens and we're in past the tokens. We want to predict future tokens, not uh, past tokens. So we want to uh, make them or make the values to be zero so that they're not like uh, being calculated with the other calculations or being added with the other calculations. But if we set them to zero, then like that causes a problem because using softmath, all these values have to add up to one. But if you add them zero just like that, the sum will be off, won't add up to one anymore. So that's why for the solution, we change the values to negative infinity before applying the softmath. So like right here, like where the values are very, very high, like negative infinity to infinity, we just set them to negative infinity. And then like we apply softmath so that we normalize the values so that we can use those values for predictions. And when we set them to zero, that's called masking. So like we're basically hiding these values. So how do we update embeddings? Well, we'll multiply the original embeddings, like these, just embeddings. We don't see the other vectors. And we multiply them with a third matrix. And that third matrix is called a value matrix. And we get a value vector. So we multiply with a matrix query to get a query vector. We multiply with a key matrix to get a key vector. And now we multiply with a value matrix to get a value vector, as you can see here. And then like we multiply that vector with the normalized ways that we obtain from the key query pairs. So like these values that we gain here from the previous steps after running softmath, we get like normalized values from 0 to 1. And as you can see, 0, 0, 0, 0, but like this is 0.42, 0.58, and those add up to 1. And so we multiply the weighted values with the vectors from the value vector. And this will basically be like a list of changes that we add to the original embeddings to get the more refined embedding that has the meaning of blue and fluffy for the creature. And we repeat this process for all embeddings, not just this embedding, but like all of the embeddings. And this is just one single head of attention. A transformer usually runs a multiple heads of um, attention, which is they run in parallel to uh, to see all the possible meanings and contexts of the sentence, because this is just one embedding for adjective. You could use attention for other things like an amount, for example, like 4 pears, 3 apples. So in addition to like the adjective attention, we could also have like an attention or like an amount attention, and and so on. We could have more than one attention. So that way we could multiple embeddings or multiple heads of attention, I mean. In conclusion, in machine learning, attention determines how the meaning of one token or word is influenced by the meaning of another. As we saw in the previous slides, each token can have a query vector and a key vector that we obtain from multiplying the respective matrices to the embedding. If the dot product of the vectors is high, then they belong to each other or they correspond to each other. In other words, the key tokens must influence the query token. Determines like attention determines how the meaning of the token influence of another? Well, a, a key determines how or like influences the query the most. Afterwards, we get a value vector and multiply it with the values of the normalized dot product. So we from the number that we get from here, we normalize it and then like we multiply with the value vector that we get, and then like we get a list of changes, and these changes are then added to the original embedding so that it reflects the more refined current embedding that has all the meaning and context of the relevant words.